We will now discuss dilute solutions and colligative properties. First, we discuss Raoult's law. The French chemist F. Raoult studied the vapor pressure of several binary solutions of volatile liquids like benzene and toluene at constant temperature and gave the following generalization known as Raoult's law. It goes as the partial pressure of any volatile component of a solution at any temperature is equal to the vapor pressure of the pure component multiplied by the mole fraction of that component in the solution. Suppose a binary solution, binary means two component system, is made of Na moles of a volatile liquid A and Nb moles of the volatile liquid B. If Pa and Pb are the partial pressures of the two liquid components A and B, then according to Raoult's law, partial pressure of component A in the mixer is XA times Pa naught, and partial pressure of component B, that is Pb, is Xb times Pb naught, where Xa and Xb are the mole fractions of component A and component B respectively. So we know that this is the expression for mole fraction. So Xa is number of moles of A divided by the total number of moles, means Na plus Nb, and mole fraction of B, Xb, is Nb divided by total number of moles of B by number of moles of A plus number of moles of B, are the mole fractions of A and B respectively. And Pa naught and Pb naught are the vapor pressure of the pure components A and B respectively. Suppose there is no other component, only pure component is there, A, then Pa naught is the vapor pressure of the pure component A. Similarly, in component B, suppose there is only one component in our system, component B, so Pb naught is the vapor pressure of pure component B. If the vapor behaves like ideal gas, then according to Dalton's law of partial pressure, the total vapor pressure is given by, so P is the total vapor pressure, is nothing but vapor pressure of component A plus vapor pressure of component B. And if we substitute the value of Pa from here to here and then Pb from here to here, we get Pa plus Pb equals to Xa times Pa naught plus Xb times Pb naught. So in general, Raoult's law can be expressed as Pi, where I is the component I is the mole fraction of component I Xi times Pi naught, means means the vapor pressure of pure component I. So the total vapor pressure may be expressed. So if we consider there are several components instead of two component system that we considered just now. So the total vapor pressure P is sum over I Pi. So this I is number of components present in the system. So what is ideal solution? Raoult's law is obeyed perfectly only in the case of ideal solutions. So this gives the definition of an ideal solution. A solution of two or more constituents is said to be ideal if it obeys Raoult's law exactly at all concentrations and at all temperatures. At all concentration means whether if you consider different proportions of A and B, then also it should follow the Raoult's law. The intermolecular or cohesive forces in these solutions are completely uniform, that is, the magnitude of these forces between the molecules is the same. For example, so it's like AA, we have pure component AA suppose and pure component BB. If we mix them, we get two component system A component A and component B. So the interaction between A and interaction between molecule B and B has to be equal to the interaction between molecule AB. Then only the solution will be ideal. So examples of binary mixtures obeying Raoult's law and thus forming ideal solution are ethylene bromide and ethylene chloride, NHN, NF10, N-butyl chloride, N-butyl bromide, benzene and toluene, etc. Next, we consider vapor pressure of ideal solutions. So the vapor pressure of an ideal binary solution of two components A and B having different mole fractions are shown in figure 1. So if we consider here, so at this point we have only pure component A, and at this point we have pure component B, and if we add more than B here, so mole fraction of component B increases in this direction. So when we have only pure component A, So the pressure is PA naught, right, that we just discussed, and when we have the pure component B, we have the pressure PB naught here. Okay. Now as we change the composition mixture here, if we keep on adding XB, okay, so the curve will look like this. So here it will be like this. Okay, so it's not properly done, so it will be like this. Okay, you get a straight line like this. Okay, so you see that as concentration of B increases, the vapor pressure of component B increases here like this, and as B increases, so vapor pressure of component A decreases. Okay, so here PB along this line, PB is PB naught times XB, and along this line PA is PA naught times XA, and the total pressure here is PT equals to PA plus PB. So here we are considering the partial pressure, or the pressure of pure component A, PA naught, is lower than PB naught. That's why the point this PA naught value here is lower than the other one. Okay, so PB naught. So total vapor pressure in terms of mole fractions of the components of the vapor phase. The total vapor pressure P can also be related to the mole fractions of the two components in the vapor phase. For notational convenience, we shall write XA vapor is YA and XB vapor is YB. So from the definition of partial pressure, we can write YA is PA by P and YB is PB by B. So where P is the total vapor pressure, hence from equation 3 here we can write XA naught times PA naught is PYA, and XB naught times PB naught gives you PYB. So if we use equation 2, so then we can write total pressure P is 1 minus XB naught, XB times PA naught plus XB times PB naught, right. So if we rearrange this one, we get PA naught plus XB times PB naught minus PA naught. So we get the mole fraction XB is P minus PA naught by PB naught minus PA naught. So using the value of equation 7 here, so if we now substitute here, we get PYB is PB naught times P minus PA naught times by PB naught minus PA naught. So here we are substituting the value of XB naught in this expression, so we get this. Or P, if we now rearrange this one, we get basically P times YB times PB naught minus PA naught minus PB naught gives minus PA naught times PB naught. Okay, so total vapor pressure P is PA naught times PB naught by PB naught plus PA naught minus PB naught times YB. So this can be simplified and put into better form. Inverting it, we have, so if we invert this one, we get this expression 1 by P is PB naught plus PA naught minus PB naught times YB by PA naught times PB naught, and if we rearrange, and then finally we get YA by PA naught plus YB times PB naught. Now let us consider the vapor pressure in equilibrium with the solution. So the mole fraction YA of component A in the vapor phase is given by the ratio of its partial pressure to the total pressure of the solution, right. Assuming that the vapor behaves ideally and Dalton's law of partial pressure applies to it. So we get YA is PA by PA plus PB, right, and then if we substitute the value of PA here, so we get this expression PA and PB. If we substitute in this expression, we get this expression, and finally we get 1 minus XB by PA naught times PA naught by PB naught minus PA naught times XB plus PA naught. Similarly, we get YB is XB times PB naught by PB naught minus PA naught times XB plus PA naught. Now consider a binary solution of component A and B forming an ideal solution. Let the activities of A and B are AA and AB respectively. Then as per Raoult's law, so PA we know XA mole fraction of A times PA naught, or we get if we rearrange this one, we get PA by PA naught is XA. Since the vapor pressure of liquid components of a solution at ordinary temperature is usually low, lying well in the within the range in which the fugacity may be taken as equal to pressure, say we can write PA by PA naught here. Okay, so you get FA by FA naught, okay, and it gives you XA naught. But we know that this ratio of this fugacity FA by FA naught is AA. So where Fa is the fugacity of component A in the solution and Fa naught is the fugacity of the pure component A. So A is the activity of the component A in the solution. So we write Fa by Fa naught is AA. So here then if we compare this and this, we get Xa is equals to AA, and similarly Xb will be AB. So an ideal solution is defined as one in which the activity of each component is equal to its mole fraction under all conditions of temperature, pressure and concentration. So this is another definition of ideal solution. So what it says, like if we take component I, so the mole fraction of component I equals to the activity of component I. Then we talk about chemical potential of an ideal solution. We know chemical potential is nothing but free energy change per mole. So consider a two component liquid solution in equilibrium with its vapor, assuming ideal. So we are considering that ideal behavior here, since for a system in equilibrium the chemical potential of component A is the same in the liquid and the gas phase. So we can write like this. Okay. So at equilibrium the chemical potential of the respective phases has to be equal here. So if liquid is in equilibrium with the vapor or gas, we can write. So for component A, mu A is the chemical potential of component A in the liquid phase. So mu A L is the chemical potential of component A in the liquid phase, and mu A G is the chemical potential of A in the gas phase. So if we write this, so we get mu A naught gas plus RT ln partial pressure PA. And for liquid A, we write mu A L is mu A naught gas phase plus RT ln PA naught. Okay. So alternatively, if we add and subtract RT ln PA naught on the right hand side of equation 19, so 19 is here, so we get mu A L is mu A naught gas plus RT ln PA naught plus RT ln PA by PA naught. So we get mu A L plus RT ln PA by PA naught. So thus there are two ways. Okay, so thus there are two ways of expressing the chemical potential of component A. Same for component B. So if we do the similar treatment, if we carry out the similar procedure here for component B, also we can write mu B L is mu B naught gas plus RT ln PB, and mu B L is mu B naught L plus RT ln PB by PB naught. So for an ideal solution obeying Raoult's law, so we know PA by PA naught is XA and PB by PB naught is XB. Thus for an ideal solution we can write mu A L. Okay, so mu A L here. Okay, mu A L here is your mu A naught L plus RT ln XA. So this would be your mu A naught. Similarly for mu B naught L, mu B L is your mu B naught L plus RT ln XB, and mu A L is mu A null mu A. So since XA equals to A activity, okay, so mole fraction equals to activity, we can substitute mole fraction by activity here. So mu A L is equal to your mu A naught L plus RT ln A, and mu B L is equals to your mu B naught L plus RT ln AB. Next, we discuss Henry's law. Although the solubility of solids in liquid is almost independent of pressure, that of gases in liquid varies considerably with pressure. So William Henry in 1805 found that the solubility of a gas at a given temperature increases directly with pressure. Hence, the Henry's law states that the mass of a gas dissolved per unit volume of a solvent is proportional to the pressure of the gas in equilibrium with the solution at constant temperature. So if m is the mass of a gas dissolved per unit volume of a solvent and P is the pressure of the gas in equilibrium with the solution, then at constant temperature m is proportional to P, or m is equals to K times P, where K is the proportionality constant. So most gases obeys the Henry's law provided the pressure is not too high, the temperature is not too low, and the gas is not highly soluble and does not dissociate or enter into chemical combination with the solvent. Thus, it is valid for solubility of hydrochloric acid and ammonia in benzene, in which both gases are sparingly soluble, but not in water, where they dissociate or enter into a chemical combination with water. Alternatively, it can be described as the pressure of a gas over a solution in which the gas is dissolved is proportional to the mole fraction of the gas dissolved in the solution. So, P2 is P2 equals to K times X2, where K is the Henry's constant, and here we are using subscript 2 because subscript 2 we are using for the gaseous solute. For solvent we use subscript 1, and for solute we use subscript 2. If Am is the mass of a gas dissolved per unit volume, this can be taken as the concentration of gas molecule in the solution phase. Since Henry's law is applicable only if gas is not largely soluble, the solution, even though standard, may be very dilute. The concentration therefore can also be expressed as proportional to the mole fraction of the dissolved substance. The Henry's law therefore may also be expressed as this. So Henry's law we can also express like mole fraction of solute X2 is proportional to the PSR of component 2. Okay, so and K prime is the proportionality constant. So we get P2 is X2 by K prime, where X2 is the mole fraction of the gas or solute in the solution which is in contact with the gas having pressure P2, and K prime is the new proportionality constant related to the K, Henry's constant K in the previous equation. We know that Raoult's law hold good in ideal solution for solvent as well as solute if both are volatile. Hence, we can take P2 as the vapor pressure of the volatile gas or solute when it is present in the extent of mole fraction X2 in the solution. So, applying Raoult's law here, now if we apply Raoult's law here in the expression of P2, so Raoult's law if we apply, we get X2, P2 is X2 times P2 naught, where P2 naught is the vapor pressure of pure solute, dissolved gas in present case at the temperature of the solution. So, equation 30 and 31 are quite similar. If you see equation 30 and 31, they are quite similar. So, here we get in the denominator K prime, and here it is multiplied by P2 naught. So, the quite similar. In fact, both become identical if K prime equals to 1 by P2, 1 upon P2 naught. So, if we consider K prime is 1 upon P2 naught, so they become identical. In that case, Raoult's law can be taken as a special case of Henry's law. Under the conditions, all solutions which obey Raoult's law must obey Henry's law. The condition K prime equals to 1 by P2 naught, however, is approached only in few cases representing ideal solution of gases in liquids. Now, so far we discussed Raoult's law ideal solution, but there are deviations of Raoult's law. Very few solutions, however, obey Raoult's law over the entire range of composition. Most of them show appreciable deviation, positive or negative, from the ideal behavior in their vapor pressures. It is called non-ideality of either the vapor phase or the solution. So, we talk about positive and negative deviation from ideal behavior. Okay, so this dotted line shows the ideal behavior. If the gases or if the components, if solution behaves ideally, then we consider this dotted line. Okay, here. Okay, so the total vapor pressure curves rises to a maximum for positive deviation, and for negative it dips into a minimum. So here it is positive deviation. This is the when the solution behaves ideally, we get this dotted line, and we get more pressure, right, at any given composition mixture compared to ideal behavior. Okay, so we get positive deviation here. So, the dotted line or dashed line represents the ideal behaviors, as I said. Also, the partial pressures of each component perform accordingly. Examples of positive deviations are acetaldehyde carbon disulfide, water propyl alcohol, and ethyl alcohol chloroform. Examples for negative deviations, here you can see the negative deviations. So, this is again the dotted line is for ideal case or ideal solution, ideal behavior, and we get the negative deviation here because the actual pressure is lower than the ideal pressure. Okay. So examples for negative deviations are acetone chloroform, water sulfuric acid, and water nitric acid. Next, we discuss lowering of vapor pressure. the addition of a non-volatile solute to a solvent at a given temperature and pressure results in lowering of vapor pressure of the solvent. At the same time, the chemical potential of the solvent is also decreased. At equilibrium, any change in chemical potential of the solvent vapor is equal to the change in the chemical potential of liquid solvent in solution. So, d mu 1 V, we can write for component 1, we can write d mu 1 L, right. The change in chemical potential, d mu 1 V is the change in the chemical potential in the vapor phase, and d mu 1 L is the change in chemical potential of component 1 in the liquid phase. The chemical potential of the solvent in solution depends upon temperature, pressure and its mole fraction. But in vapor phase, it depends only on temperature and pressure. So, we can write mu 1 L is function of temperature, pressure and the mole fraction of component 1, because we are considering component 1 here. But mu 1 V means chemical potential of component 1 in the vapor phase, it is function of only temperature and pressure, not on the mole fraction of the component 1. So, d mu 1 L, if we do the differentiation, we get del mu by del 1 by del T for in the liquid phase. So, when pressure and x1 is constant times dt, and then if we differentiate mu 1 with respect to del P, we get this expression, we get this term here. Okay, here temperature and the mole fraction of component 1 are fixed, and if we differentiate partial differentiation here, if we differentiate del mu 1 by del x1 at constant temperature and pressure times dx1. So, but from thermodynamics we know, so del mu by del T at constant pressure gives you S1, okay, so minus S1, so absolute entropy of component 1, and del mu by del P L at temperature when T is constant, we get minus volume, okay, where V and S are the partial molar volume and partial molar entropy respectively. So, we can write, so this V will be positive sign here. So, we can write del d mu L is minus S1 here, minus S1 dt plus V1 dP, and this is the term, okay, d mu 1 by del x1 at when temperature, pressure are constant times dx1. So, for an ideal solution, we already discussed, for an ideal solution mu 1 L is mu 1 naught plus RT ln x1. So, if you differentiate this one with respect to x1, we get RT by x1, right. So, del mu 1 by del x1 at constant temperature and pressure gives RT by x1. So, at constant temperature and pressure assumed to be 1 atmosphere, when pressure is assumed to be 1 atmosphere, we obtain from equation 36 and 38. So, 36 was our this expression and 38 is this expression. So, if we combine them, we get del mu d mu 1 L is RT dx1 by x1. Since at a given temperature the chemical potential of vapor is affected by a change in pressure, so we have d mu 1 V by del mu 1 by del P times at constant temperature and x1 times dP gives V1 dP. Since for an infinitely dilute binary solutions, so we can write V bar means molar volume equals to V. So, we can write this is V1 times dP. So, assuming the ideal behavior of an ideal gas, so V1 is nothing but RT by P1. So, if we substitute it here, so we get d mu 1 at for the vapor phase is RT by P1 times dP. Now, at equilibrium, change in chemical potential of component 1 in the vapor phase equals to change in component 1 in the liquid phase. So, we can write, so we just equate them. Okay. So, if we equate them, basically this one, this term and this term. So, if we equate them, we get RT by P1 times dP equals to RT by x1 times dx1. Okay. So, we are just equating this term and this term, 39 and 42 here. Since for binary mixture, so total mole fraction means mole fraction of component 1 and mole fraction of component 2 will give you total mole fraction, that is 1. So change in mole fraction of component 1 plus change in mole fraction of component 2 gives 0. So change in mole fraction of component 1 will be negative of change in mole fraction of component 2. Here the subscripts 1 and 2 refers to solvent and 1 refers to the solvent and 2 to the solute. So equation 43, so this equation here, so it becomes RT by P1 dP minus RT1 minus X2 dx2, or dP1 by P1 gives you minus dx2 by 1 minus x2. Now equation 46, if we consider the limit, so when x2 is 0, okay, when the solute there is no solute there, so the pressure will become the P1 naught, right, and when x2 becomes x2, the pressure is P1. So we get ln P1 by P1 naught is ln 1 by x2. So P1 by P1 naught gives you 1 minus x2 or x1, or P1 gives you x1 times P1 naught. So this is the Raoult's law, okay, that we already discussed. Now if we see this equation of 49 here, so this 49 we can also write P1 naught minus P1, if we rearrange this one, we get by P1 naught gives you x2. So P1 naught and minus P1, the numerator is nothing but vapor pressure lowering, and if we divide it by P1 naught, then this is relative lowering of vapor pressure, okay, or relative vapor pressure lowering, okay. So P1 P1 naught minus P1 is the vapor pressure lowering, and P1 naught minus P1 by P1 naught gives the relative vapor pressure lowering. So we see that the relative vapor pressure lowering is proportional to the mole fraction of the non-volatile solute in solution. So you can see this relative lowering of vapor pressure is proportional to the mole fraction of the non-volatile solute in solution. It is independent of the nature of the solute. So it does not depend on what kind of solute we are taking. It depends only on the mole fraction of the solute. Hence, such a property is called colligative property. What are the colligative properties? They are the properties that depend entirely on the number of particles of the solute dissolved in a known volume of a given solvent, and not at all on the nature of the solute. So it depends only on the number of solute particles present, okay, in a given solvent. Now the mole fraction x2 we know N2 by N1 plus N2. So for a dilute solution, the number of moles of the solute N2 can be neglected in comparison to N1. So when we consider dilute solution, means solute is present very small amount, so we can actually neglect the term N2. So we get N2 by N1. So in comparison to N1 we can actually neglect N2. So the number of moles of the solvent N1. So we can write x2 is nothing but N2 by N1. Now what is N2? N2 is the number of moles of solute. Okay. So number of moles of solute is weight of the solute W2 by the mole fraction or molar mass of the solute M2, and N1 is weight of the solvent W1 by divided by the molar mass of the solvent. Okay. So if we rearrange, we get x2 is W2 M1 by W1 M2. So where W2 is the amount of the solute dissolved in W1 amount of the solvent. So M1 is the molar mass of the solvent and M2 is the molar mass of the solute. So we can also write P1 minus P1 naught here. So P1 naught minus P1 by P1 naught gives you x2. Now x2 we got W2 M1 by W1 M2. Okay, so we arrive at this expression. Okay, so next we consider elevation of boiling point. The boiling point TB of a liquid is the temperature at which its vapor pressure is equal to the atmospheric pressure. So when a non-volatile solute is added to a liquid, the vapor pressure is decreased. Hence, it must be heated to a higher temperature so that its vapor pressure becomes equal to the atmospheric pressure. This means the addition of a non-volatile solute brings about elevation in the boiling point. So we have already seen that when liquid phase is in equilibrium with the vapor phase, for component 1 for the solvent here, because solute is non-volatile here, we are considering solvent. So we can write d mu 1 at vapor phase equals to d mu 1 at liquid phase. Now we also know that okay, mu1 liquid, so chemical potential in the liquid phase of component 1, it depends on three factors, T, temperature, pressure and x1, and three variables here, and mu1 V, it depends on two variables, temperature and pressure here, and d mu 1 L is d mu, this one we also got, so del mu 1 by del T at when pressure constant and number of mole fraction is constant times dt, del mu 1 del P when T and x1 constant times dP, and del mu 1 by del x1 for liquid phase when temperature and pressure constant times del dx1. And d mu L we already know, that is minus S1 L plus B1 L dP, S1 times dt minus plus V1 times dP plus del mu 1 by del x1 times dx1. And for the vapor phase we know this is S1 dt plus V dP in the vapor phase. Here it will be minus sign again. So we can actually at equilibrium, since d mu 1 in vapor phase equals to d mu 1 in the liquid phase, so we equate this equation with this equation. If okay, right? So if we equate them, so we get this expression, okay, here. Now if we rearrange, if we take the entropy term this side, we arrive at this expression. Okay. So what it says is S1V minus S1L dt plus V1L minus V1V dP equals to minus del mu L by del x1 Tp times dx1.